What am I wearing? Hello, and welcome. Yes, no, I don't know why I own this. It's a thing. When I put it on, my my wife said that I looked like a '70s game show host. I guess I'm doing my best, Bob Barker impression here, or maybe Don Cherry, if you're familiar with Don Cherry, a hockey host. Although I've got nothing on Don Cherry. But with that out of the way, this is what I hope it doesn't distract you too much, but it's what I'm wearing today. So we're on to what we're doing today. What I have for you today is actually two split topics. The first one is the Doppler effect, and the second one is standing waves. So standing waves are really what's going to carry us into our next part of the unit. But I figured we should go ahead and talk about the Doppler effect because it's really interesting and it's related to waves. And so here's a place that I thought was good to slot it in. So I'll actually start with the Doppler effect. But the Doppler effect should sound familiar if you don't know what it is already. But before defining it for you, I want to do a little experiment with you. So I want you to, wherever you are, no matter wherever you are, seriously, to make aloud a noise to imitate a car that drives past you. I'm serious. Make the noise of a car driving past you. Yes. What you should have made during that time period is a sound that sounds like something like this. Right? That's the sound of a car driving past you. That's the sound they make. So what are you actually hearing when that sound is being made, right? What sound is the car, what's producing the sound? Well, it's the car's engine is making the noise, right? And some of it is the air that's rushing around the car. So my question is, why does that sound change pitch as the car drives past you, right? Because it goes from a high pitch, the nee, to a low pitch with the right? It goes from high to low pitched. So why does that sound change? Is the motor making a different noise as it drives past you? Does the wind change as the car drives past you? No, right? The motor, if you're sitting in the car, the motor sounds the same the whole time. You don't hear it change noises when it drives past someone, right? So why does that happen when you're outside of the car and standing still? Well, it's actually due to this thing called the Doppler effect. So the Doppler effect is a phenomenon in which it causes a sound to change pitch based on the motion of either a source of sound or an observer of the sound, right? Either the thing making the sound or the person hearing the sound is moving, and so the pitch changes. Don't worry too much about the understanding the definition if that sounds confusing, because I've got a couple of simulations for you to look at. So here's the first one. So on the left there, you've got your sound source, the thing that's making the sound, and on the right, that's or the source is like the car, and on the right there is the observer, who is like us, standing on the side of the road listening. And so watch what happens when I start this up. So whenever I press start, the source starts emitting sound waves. That's what those circles are that's moving away, right? Those are the waves of sound that's being emitted by the source. And you see that when they hit the observer, right, they're hitting the observer at a certain frequency, right? They're passing over the observer at a certain rate or a certain frequency. And in previous lesson, we learned that frequency of a wave is related to pitch, right? Frequency and pitch are related. So the observer's hearing a certain pitch because there's a certain frequency of waves passing over him. Now, this is with the source standing still, right? But I'm going to show you what happens when the car drives towards you, right? So whenever I change the speed to where it's moving towards the observer, watch what happens to the waves. You see that as it's moving and emitting sound, the waves are bunching up in the front of it, right? They're closer together in the front because it's moving and it's moved a little bit in between emission of the waves, right? So they're closer together on the front end. They have a higher frequency on the front end, right? So they're making a higher pitched noise. And on the back end, notice that they're further apart. They're more spread out, right? So the frequency is lower, meaning we have a lower pitched sound. So as the car is driving towards you, it's making a higher pitched sound. And as it's driving away, it's making a lower pitched sound. The right? It's because as it's moving, it's pushing the waves together on the front and spreading them out on the back end, right? That's the Doppler effect. the change in pitch caused by motion. So if something's moving towards you, it's going to sound higher pitched. If it's moving away from you, it's going to sound lower pitched. Very interesting. So that's with us just standing still. But we can actually adjust from here. And I've got a couple of scenarios to throw your way. So scenario 1, we've got what we just experienced, where we've got the observer who's standing still, and the source is moving towards the observer. Scenario 2 is the source is moving towards the observer, and the observer is moving towards the source. Okay? And scenario 3, we have the source still moving towards the observer, but this time the observer is moving away from the source. Got it? So my question is, in which case is the frequency the highest? In which case is the frequency the highest? Is it the stationary observer? Is it observer and source moving towards each other? Or is it that the source, is the observer is running away from the source? It's scenario 2, right? Where they're moving towards one another. So the source is still moving towards the observer, right? So we decided that when a car is moving towards you, it's making a higher pitched noise. But if you notice that as the observer is moving towards the source, it's causing the observer to experience the waves even faster. They're running into waves faster than if they would be standing still. So in the case of scenario 2, that's our highest pitch, because you can see that the observer is experiencing the highest frequency of waves. So it looks like observer movement counts as well. For contrast, I didn't list it here as a scenario, but imagine the source and the observer are moving in opposite directions, right? So the car is moving away from you, meaning it's making the lowest pitched noise, but also you're going the opposite direction. So the car would be making even lower pitched noise. That's our lowest possible pitch, is when they're moving away from each other, right? So yeah, that's kind of all there is to the Doppler effect. But it's very neat, very something you experience in everyday life. So now show off to your friends and family about why why the meow sound happens, and you can explain it. So that's all for the Doppler effect. Pretty quick wrap up for that one. But that brings us to our next larger topic. Well, the intro to our next larger topic. So previously we saw how individual wave pulses interfered with one another when they ran into each other, right? Either constructively or destructively. So what I've got, the question that leads the next part of our discussion is, what happens when continuous trains of waves interfere with one another, right? A train is multiple wave pulses, back to back to back. So what happens when trains of wave pulses interact? And I've got another simulation for you. This one courtesy of Physics Classroom. The first one was from O Physics for the Doppler effect, but this one's from Physics Classroom. This one's really good. So on Physics Classroom, you've got this simulation that has wave 1, wave 2, and then the resulting wave, wave 1 plus 2. So take a look. Whenever we start it up with just 2 random waves that are continuous, right? Look how crazy that resultant wave is, the 1 plus 2 wave. It's oscillating all over the place. You see, like, there's bigger waves inside the smaller waves, right? You see the individual up and down, but the individual up and downs have like their own up and downs with the interactions that are going like that. So it looks kind of crazy, but you see that there's like larger fluctuations. So we actually can tweak this a little bit more. These are just 2 random waves interacting with one another. But what happens when waves that have the same frequency and wavelength collide while moving in opposite directions? So it's the same wave comes from this way as this way, and they line up and they collide. What happens then? Let's see. So whenever I adjust this wave here to make them the same wavelengths, we create this wave, which looks different, right? So in this wave, you just have things moving up and down, right? There's no observable left and right motion here, right? It doesn't look like the wave is traveling left to right. You just see the individual waves moving up and down. So this type of wave is a special type of wave called a standing wave. Standing because it doesn't look like it's traveling, right? Now we see here that it's actually 2 different wave trains traveling in opposite directions, but the resultant wave looks like it's not moving. It looks like it's one standing wave. So this special kind of wave is what we'll be using, looking at in the rest of this unit. And I wanted to point out some anatomy of the standing wave to you. So the standing wave, there's two obvious points. There's the big peaks that move up and down, right? And then there's actually points that don't look like they're moving at all. So the big parts that are the parts that are staying still and not going anywhere, like right here, that's called a node. A node is a point where the wave doesn't appear to be moving. The standing wave doesn't appear to be moving. And then the part that's moving up and down, right here, is called the antinode. It's the opposite of a node, right? Node and a not node is what those are. So what you're seeing here on this next screen with the labeling, this is so previously they were moving up and down, right? But when you see like on a written paper depiction of a standing wave, you just see them written on top of one another. It's two possible positions. So this is what a standing wave will look like when written out on a piece of paper, right? You've got it just in its two maximum positions, where you've got the node here and the antinode labeled as well. So this is what like a paper depiction of a standing wave looks like, because we can't draw that obviously at moving. So this is a standing wave, node, antinode. Neat. So what's really important for the next part of our unit is actually something that you could sort of see in the previous lab that we did, but I wasn't pointing out. So in the Slinky lab that I was demonstrating when I was making waves, you could actually see that whenever I made a wave, either transverse or longitudinal, that the waves bounced back. So when waves hit a hard surface, they actually reflect. If you've ever done this in like a pool, right, where you kind of can splash a wall and the waves will bounce back. So when waves hit a hard surface, they reflect. So imagine a source. We saw this simulation from physics classroom where the oscillator is making waves and sending them out of a window, in this case where there was no end, but we can actually change this simulation to where it hits a hard surface. So if it hits a hard surface like this, the waves bounce back. And so if waves are bouncing back at just the right rate, at just the right frequency, you can actually make a standing wave using just a single source. It doesn't have to be two separate waves. So you can make a single standing wave, or a standing wave from a single source. And this is the concept that musical instruments use, for example, that we'll be looking at in the following lessons. And this is kind of like the big launching point for the rest of them, is that you can make a standing wave based off of the reflections of an individual wave source. And so with that, that's really the end of this one. There's more to cover on standing waves. I just didn't want to overwhelm you in this video with it. So this one is a relatively short one, but the standing waves will be covered more in the next lesson. So I hope you enjoyed that, which is this nonsense. I also had to keep this short, right, or I'd be too distracting in my suit. So be excited for next one, which we cover resonance and harmonics in. So this is Bob Barker signing off.